In your school days, you must have come across this constant, pi. It is a very special number. By definition, pi is the ratio of a circle's circumference to its diameter. No matter how big or small the circle is, the ratio never changes. You might also remember another strange fact about pi. It is an irrational number. That means it never ends and never repeats. You can keep writing digits forever. The earliest known accurate calculations of pi was done by this absolute legend, Archimedes. Using nothing but geometry and sheer patience, he managed to approximate pi to 2 decimal digits. Now, this took him months of work, but I don't have months. I don't even have minutes. I have a single second. So how do we calculate pi in a second? One of the simplest approaches is the Monte Carlo method. Imagine a square and inside it a perfectly inscribed circle. If we randomly throw points into the square, some will land inside the circle and some will land outside. The ratio of these two numbers will be proportional to the ratio of the area of the circle and the square. Let's write a quick program. We generate points using the rand function, count how many fall inside the circle, and return the value of pi. Except when we run it, the result is kind of embarrassing. We barely get 2 decimal digits of accuracy. We can see that we generated around 80 million points. The Monte Carlo method depends on two things: the number of points we sample and the quality of these points. The next logical step is to increase the number of points we sample. Compiling with O3, we get a nice performance boost. Interestingly, however, our approximation of pi does not improve. Why? The error is proportional to the inverse square root of the number of points we sample. So although we went from around 80 million points to 360 million points, our error only improved marginally. What can we do to fix this? Well, the issue with random sampling is that we form clusters. Some regions are oversampled while others are undersampled. This causes a high amount of variance, leading to more error in our approximation of pi. To fix this, we can split our square into a grid and sample points inside each of these small squares. This eliminates the issue of clustering. This approach gives us 3 digits of pi. But can we do better? So far, we've pretty much been gambling. If only there was a way to calculate the area of a curve directly. So given any circle, we know its equation. X square plus y square is equal to r square. Now we can rewrite this to get y in terms of x, and upon integrating this, we get the area of the circle. But the issue is we cannot solve this exactly without using a symbolic solution. But thankfully, we don't have to. We can use a numerical approximation. We divide the interval into evenly spaced segments and approximate the curve using parabolas. This is known as the Simpsons method. Here I've written an implementation of pi Simpsons in C. Now upon running this, we find that in a single second, we got 7 digits of pi, which is pretty impressive. Now, we could optimize this further, but I want to calculate hundreds of digits of pi, and optimizations won't get us that far. If only we had a formula for pi. Alright, we do! Based on Ramanujan's work, the Chudnovsky algorithm was devised. This algorithm is the fastest way to calculate pi. Each term gives us 14 correct digits of pi. Such a powerful algorithm is honestly easier than expected to implement. We do have to move to Big Float, a custom data type that supports large floating point numbers. Okay, now let's compile and run this behemoth. I've written a binary search to check how many terms we can calculate in 1 second on my computer, and it appears we can calculate around 480 terms, and that gives us 6,750 digits of pi. When I ran the test before recording, it gave me around 7,000. So I would assume the loss is due to OBS running in the background, but that's still pretty impressive. So at the end, we got around 7,000 digits in a single second. It took Archimedes 2 months to calculate 2 digits, and it took us a single second to calculate 7,000. If you like this video, subscribe, like, share, whatever. Bye bye.